Presented here are two conservation of energy problems. The first problem says that a mass is held some distance above an uncompressed spring with a certain spring constant. The mass is released, implied that it's released from rest, and falls onto the spring and compresses it. How far does the spring compress? So first we should ask ourselves, is energy conserved? Right? Can I really use conservation of energy here? And the conditions are that there can be no external forces on the system, and it doesn't look like there are. Right? We're going to include gravity. Right? Clearly, gravity acts on this ball and also on the spring. But we include gravity as gravitational potential. So we're including the Earth as part of the system, and gravity is an internal force. So that doesn't count as an external force. So really we're asking, is there any friction? Well, there's no friction. But that's not enough to specify that energy, mechanical energy, is conserved. So the other question is, are there any non-conservative forces? Again, are any of the internal forces friction, basically? And as long as when we compress the spring, it doesn't heat up very much, then yeah, all of the forces here are conservative, right? We've got gravity, and we've got a spring force. So we really can say that E initial equals E final. Okay, so we'll write down E initial. Looks like we can call this our initial state. We can call this our final state. So we could write K initial plus UG initial, that's gravitational potential, plus US initial, that's spring potential, equals K final plus UG final plus US final. So we should recall here that gravitational potential UG is mgh, mass times 9.8 times the height, and spring potential US is 1/2 K times a delta x squared, where delta x is the distance that the spring is compressed or stretched from equilibrium. Right? So in the initial state here, we're in equilibrium, the spring is not being pushed at all, and in the final state here, it's been compressed by delta y. So in this case, delta x will be delta y. So let me put a little box around those. Okay, so some of these terms are zero. Initially, it's starting from rest, and when it has compressed this spring, it's also at rest. So both of the kinetic energies are zero. Right? Clearly, it gains and loses kinetic energy in this process. It gains kinetic energy until it hits the spring, and then loses that kinetic energy. But because we're not choosing any point while it's moving, I don't actually have to include it. So also, the initial state, the spring is not compressed, so delta x in that case is 0. So this looks like what we should include. So we'll say this, mgh initial equals mgh final plus 1/2 k delta y squared. Right, and that's just because we have the spring tilted so that the displacement from equilibrium is in y direction. So it doesn't really matter what we call it, but we'll call it delta y. So let's identify what are h initial and h final. And really to identify that, we need to decide what we're going to call h equals 0. It doesn't really matter. Let's just call this position h equals 0, which means that the initial height here, h initial, must be 1 meter, right? And h final is minus delta y, right? We're below what we've called 0, so it's going to have to be negative. And we'll plug that in when we do that. So let's fill out some numbers here. The mass is 2.5, and it's grams, so it's times 10 to the minus 3, times g is 9.8, times h initial, which is 1 meter. And that equals the same 2.5 times 10 to the minus 3 times 9.8 times h final. H final is minus delta y, right? Because we're below what we've called 0 by delta y. And then it's 1/2 of k. K we're given is 7.5. So 7.5 times 1/2 times delta y squared. Okay, so the only thing we don't know here is delta y, and it shows up twice, right? Once as a square and once to the first power, and then we have a constant term on the other side. So we're going to rearrange this and solve a quadratic equation. Okay, so if we multiply this out and move the constant to the other side, we can write 0 equals 3.75 times delta y squared minus 0.0245 times delta y minus 0.0245. I've left off units here for convenience. It's a good idea to multiply that out, but if we did everything right in this step, these numbers should all work out to the correct units. So if you plug this into the quadratic formula, or you use your calculator to solve it, you get 2 answers, right? You should get 2 answers anytime you have a quadratic equation. So the 2 answers you get are 0.0842, rounding a little bit. You also get minus 0.0776, and those numbers are both in meters because we plugged everything in SI units. So now we can use the physical situation to tell us which one of these is correct. We defined delta y to be a positive value, right? Because h final was negative, so we put a negative explicitly in this equation. So delta y is positive. So this answer, this minus 0.077, that doesn't make any sense. So that can't be the right answer. So then the answer must be 0.084 meters, or converting that to centimeters to make it pretty, 8.4 centimeters. Right, so then we can ask, does that seem reasonable? Well, yeah, we're dropping a small mass from a pretty high height onto a spring that has kind of a lower spring constant. So, yeah, this seems to make sense. So the second problem here has a rod with a specific length, and it's tipped over so that it rotates around its base. So this is our axis of rotation here, so we'll label that. Axis of rotation, right? So the question is, how fast, meaning what linear velocity, is the end of the rod traveling when it hits the floor? Right? So in this figure here, it hasn't quite hit the floor. It's going to keep traveling until it's completely horizontal. Okay, so again, we can ask, is energy conserved? Well, there's no friction here. We're assuming it's not slowed down by the air because it's not going to go fast enough. So the only force is gravity. So as long as we include gravitational potential, there are no external forces. So we can write E initial equals E final. Okay, so that means kinetic initial plus U initial equals kinetic final plus U final. Okay, so we can cross a couple of these off. Right when we give this thing a little bit of a tap to fall over, it's not moving, right? Or right before that, it's not moving, so kinetic initial is 0. And once it hits the ground, all of its mass is at h equals 0, so U final is also going to be 0. Okay? So we can write, well, we should inspect this a little further. K final, clearly it's moving as it hits the ground, right before it hits the ground. But it's not moving in a linear fashion, so you should recall that you can write down the energy or the kinetic energy of something that's rotating as 1/2 times the moment of inertia times its angular velocity squared. Right? So this is the energy that it has when it hits the floor. And then U initial is going to be mgh. But we need to be careful here. The h is not equal to L, right? Because not all of this mass is located L above the ground, right? Some of it is not above the ground at all. Some of it's only part way. So we can do something similar to what we did for rotation or gravitational torque, right? Which is to say, we can treat it as if gravity is all acting at the center of mass. Right? So this right here is the center of mass. So h is going to be this distance, so it's half of the length. Okay, so then the other things we need are, we need the moment of inertia for a bar rotating around one end. So we'll write that here. Recall that the moment of inertia I for a bar, specifically rotating around one end, is 1/3 ml squared. Okay, and we need to relate omega, the angular velocity, to the linear velocity that we care about. So you'll recall that the tangential velocity for something that's rotating is equal to omega times the distance of that linearly moving part from the axis of rotation. So that's this distance here, r, and it looks like r equals L in this case. Okay, so now I can take all of these bits of information and fill out this equation. So the mass of this object is what I'll call a capital M. So that'll be mg, h is half of L, so that's L halves, equals 1/2 times I is 1/3 ml squared, and omega is V over R, and R is L. Okay, so that's V over L squared. Okay, so before we start plugging numbers in, it'll help us to see what we can cancel out. In fact, we're not given a mass, but you can see that it doesn't matter because I have a mass on this side and a mass on this side. I can just divide it and it goes away. You'll also notice this L squared and this 1 over L squared can cancel out, right? L squared. And it's also useful to notice that I have a 1/2 here and 1/2 right here. So if I collect the only things that are left and solve for V, you'll see that it's simply the square root of this 3 moved to the other side. So there's a 3, a G, and an L, 3GL. Okay, so I can plug those numbers in here. 3 times 9.8 meters per second squared times 3 meters. Right. That works out to 9.4. And we'll look at the units. I have meters times meters, so that's meters squared per second squared, and the square root of that is simply meters per second, which is what we expected. So we can ask, is that reasonable? Well, this is a 3-meter rod, so it's pretty long. So even small omegas will result in fairly large velocities at the very tip of this. Right? So yeah, this is probably not unreasonable for when this thing hits the floor.